friction problems here in this video. I'm doing this to get a little bit ahead. Most people have seen friction in their Physics 1 classes, and we have two example problems in the lecture notes that I thought I'd just kind of get through here really quickly so that we can close out friction pretty quick here and move on to the last couple topics for the class, which is centroids, area moments of inertia, and mass moments of inertia. So I have two example problems that we're going to do. I'm going to put you over on the writing pad here right now, and we will get to it. Okay, so we should all be able to see the practice problems here now. If you want to speed me up, maybe you could go to 1.5x or something like that to get through this a bit more quickly, but all right, here we go. We've got a 6.5 meter ladder leaning against a wall. Assuming that the wall at B is smooth, here's point B, is smooth. That means that there is no friction up and down here at point B. Determine the smallest value of mu sub s between the ladder and the ground at A, for which equilibrium is maintained. Assume an unknown weight of W acts at the center of the ladder. Okay, so this is a friction problem where we've got this ladder 6 meters tall, 2.5 meters sort of wide as we have right now. Point A, there is friction. At point B, there is not. We're told it's smooth. And so we can think about then, given what we know, doing a free body diagram of this and trying to solve for what is the value of the static coefficient of friction required so that this thing does not move, so it stays in equilibrium. So here's a free body diagram, and there's a strategy in the set of slides that you can sort of take a look at that we're going to enact here. But more or less, we're going to do a free body diagram just like we do basically for everything. We're going to assume that we are in equilibrium, that it is not moving. Okay, so here we have, I'm going to label this as N, the normal force at A. And we have a wall here at B. Just because it's a smooth wall doesn't mean that the wall doesn't give any loads at all. It's still stopping the ladder from moving to the right at B there. So I'm going to label this as force at B in the X direction. We have a weight. It's an unknown weight acting in the center. I'm going to label this as W. And now at point A down here, we're told that there is friction. At point B, there's no friction. So at B, we're kind of done. We got to think about at A. This ladder, it's kind of on the brink of sliding out, or we're asked what the coefficient of friction required would be so that it does not slide out. So we're looking for the minimum value. And if this was going to slide out, you could imagine that point A kind of wants to go to the left. So that means the friction force is going to oppose that, meaning the friction force is going to be here to the right. I'm going to label this as FF. And this is our full free body diagram for this situation. All right. I'm going to make a couple notes here. To find this mu sub s, we're going to assume that the ladder is just about to slip. Okay, and then we're going to solve for that value. If the ladder is just about to slip, that means that the friction force is the maximum static friction force, right? We talked about this in the lecture notes. And the maximum static friction force that you can have is mu sub s times the normal force. So that is one piece of information that we have that's kind of going for us. You could plug that in straight away here if you want for FF. I'm going to kind of work through the problem with FF as it is, and then plug mu sub s in a little bit later. All right. So let's go now with our equilibrium. Let's sum the forces in X. We sum the forces in X equals 0. We have the friction force pointing to the right, and we have Bx pointing to the left. Okay, so these and these are going to be equal to 0. So this together tells me that Fbx is equal to the friction force. And we know over here that the friction force is mu sub s times the normal force. So I'm going to put that in here straight away. If we're right on the verge of slipping, that means we're at the position where the friction force is the maximum that it could be just before slipping occurs. That's mu sub s times n, right? Now, we have a bit of a sticky situation here because we have this weight W, which is actually unknown. So the next step I might do in my free body diagram is do some of the forces in the Y. but I'm just going to get that NA is equal to W. And honestly, that's not all that particularly helpful for us here. Instead, well, yeah. Instead, I think it might be a bit more useful to sum the moments about some point on the structure. All right. So let's sum the moments about W equals 0. Yeah, we could do some of the forces Y. We'll probably need that eventually anyway. But all right, let's stand here at the center. I'm saying some of the moments about W. It's really about the center of the ladder. But let's sum the moments here. All right, we have some contribution from FBX, and we have dimensions in this problem. This ladder is 6 meters tall. So if the weight's right in the middle, we know that we have 3 meters to FBX. All right, so we have a positive contribution. So 3 meters times FBX. That's the contribution from that guy. I have a contribution from the friction force. Again, I'm 3 meters from the line of action of the friction force. So again, a positive contribution. And then I have this normal force at A. It's going to be at half of this distance, right? It's half of the horizontal distance, which is 1.25 meters. And this will be a minus contribution. All right. So here's my sum of the moments about the weight, the center. I can make some substitutions here. I know FBX and FF are both equal to mu sub s times n. So both of these guys here are mu sub s times n. So I can make those substitutions here. So I have 3 mu sub s times n, and this is NA, if that's not clear, plus 3 mu sub s times NA minus 1.25 NA equals 0. Interestingly, each term contains an NA, so we can actually eliminate NA from this equation. Divide everything through by NA, that all actually kind of goes away. So what you're left with here is 6 mu sub s minus 1.25 equals 0. A bit slick, but here mu sub s then must be 1.25 over 6, which in decimal form here is 0.208. And that's the value. That is the minimum value of mu sub s required to keep this ladder in equilibrium. That's the end of this problem. There were some very strategic choices about where we made the moment. And, you could go through this with some of the forces Y as well. You'd have a W hanging out around there for quite a long time, but eventually it would cancel out and you would understand and get to this particular point. So that's that example problem, kind of determining what's the minimum static coefficient force required for equilibrium. Okay, we have one more problem that we're going to work through here, and that is from slide 13 in the deck. And I'm guessing maybe many of you have seen problems that look like this in your physics class. This is like a very kind of famous classical kind of physics type problem. But we're going to attack it from a sort of a statics point of view. All right. So here we got a 120-pound cabinet. We know the weight now. Mounted on casters that are both currently locked. Okay, so we have casters here and here. They're both currently locked. Determine the coefficient of static friction between the floor and the casters. I'm sorry, it is 0.3. We want to determine the force required to move the cabinet and the largest allowable value of H if the cabinet's not to tip over. So we have two possible situations here. One, the cabinet moves linearly against the ground. And two, the cabinet tips over, kind of pivoting around point B, it would be. So let's look at sort of the first bit first and determine what force P would be required to cause linear motion. So here first, for linear motion, what value of P is required? All right, so let's do a free body diagram with a full cabinet, assuming that we're going to have sort of linear motion, meaning that both casters remain in contact with the ground. So free body diagram here. Here's my cabinet. I have my force P pushing to the right. I've got the weight of the cabinet down. We're actually given what that is, 120 pounds. And we have forces at A and B. So obviously there's a floor, which will stop the cabinet from moving through it. So here, this is point A. We have a normal force at A. I'm going to label that as NA. Also on the far right, we have a normal force at B. And also, if both of these casters are locked, they will both be contributing some amount of friction force to stop this cabinet from moving to the right. So we're going to have two friction forces to the left. I'm going to label this as FFA and FFB. Now it looks like we have more unknowns than we can handle here, but it's not really true because we know that if we're just about to move, then these friction forces are reaching their maximum values. Otherwise, they would stop the motion, right? So they're sort of reaching their maximum values. We know the maximum static values are mu sub s times the normal force, so mu sub s NA and mu sub s NB. Okay. Now, let's do our equilibrium for this situation. Here we go, sum of the forces x equals 0. Actually, let's start with sum of the forces y. I think it's more instructive to look at sum of the forces y first. Okay, so here we go, sum of the forces y. We've got the weight acting down, and we have NA and NB up. Okay, I'm going to rearrange this slightly in a strategic way that we're going to use later. NA plus NB equals the weight. I think this is kind of a intuitive understanding of just the physical world and what has to happen, is that whatever force the floor applies to the cabinet has to be equal to the weight, as long as that force P acting is completely horizontal. So, the weight of the cabinet is held up by the reactions in the y direction at the two casters. That sort of makes complete sense, right? Okay. So we're going to use this a little bit later. So we're actually going to kind of use it right now. So here, let's look at some of the forces in the x direction. Okay, we've got P acting to the right. I'll move this up a little bit so you can kind of remind yourself what the diagram looks like. P acting to the right. And then we have minus the frictional force at A minus the frictional force at B. And that's it. I'm going to rewrite this slightly as the frictional force at A plus the frictional force at B, kind of grouped together. Much in the same way that the normal forces had to restrict the weight, the two frictional forces are sort of restricting the force P that acts to the right. I can make my substitutions for the frictional force at A and the frictional force at B. I know they both need to be the maximum if motion is impending, so we kind of saw that up there. We have P minus mu sub s times NA plus mu sub s times NB equals 0. I'm going to again make a grouping, P minus mu sub s times the quantity NA plus NB. Okay, that's just rearranging that guy right there. And I think you see the slick trick now. Normal force at A plus the normal force at B is equal to W. So I can replace this with W. Very, very slick. So in that sense, P minus mu sub s times W is equal to 0. Weight I have, mu sub s I have, the weight is 120, mu sub s is 0.3. So we can solve this and get that P will be equal to 36 pounds. So if you apply this horizontal force to the cabinet, it will start sliding. Cool. The last part of the problem asks us about what height, if that force P is applied, would actually cause this thing to start tipping. And that requires just a little bit of tricks in understanding about what's going to happen with this cabinet right before it starts to tip. Let's go back up here and look at the problem statement. What is the largest allowable value of H if the cabinet is not to tip over? Notice that the variable H didn't come into play when we were thinking about what was the maximum value of P that would cause linear motion. That's only because we did some of the forces X, some of the forces Y, and that's it. Here now we got to think about, all right, if that force P is applied at a certain height, this cabinet could tip over. I think we kind of all have sort of experienced that in our life. So how do we approach this portion of the problem then? So here, what about tipping? What I ask myself when I'm standing at a kiosk at every coffee shop. What about tipping? Okay. We know that if the force P is greater than 36, this will slide, regardless of the value of H. So it doesn't matter where I apply P vertically if I'm just thinking about whether or not the cabinet will slide. So what that means is the maximum load P that I could possibly apply is 36 before it starts moving. So what I want to do now is say, all right, let's assume that we have 36 pounds acting. We're just on the verge of sliding, but instead we're going to enact the fact that it's tipping. So let's say, let's find value of H with P equals 36 pounds. That would cause tipping. Okay. So in this scenario that we're looking at, we're basically saying 36 pounds is being applied, and there's a 50-50 chance that it's going to tip or slide, more or less. It's the Schrodinger's tipping problem. All right. So if it tips, what's going to happen? Well, what's going to happen if it starts tipping is that point A is going to release from the ground. So point A will lose contact from the ground. And remind you what the figure looks like. Here's the cabinet. If this thing is about to sort of tip over, that means that point A needs to release from the ground. If point A is releasing from the ground, it does not provide any normal force, it does not provide any frictional force. So that changes our free body diagram. And now we are going to look something more like this. And I'm actually going to incorporate the variable P at its height. So here's P. I know this is going to be 36 pounds. Here's W. The W remains unchanged. It's 120 pounds. I have this normal force at B, and I have the frictional force at B that resists motion still. And no longer do I have anything at A. I'm about to lift off, or I'm just lifting off, meaning that I have lost contact at A. I can't have any load transfer there. Okay? So this is the sort of setup that we have here. All right. Where's my equilibrium? And I'm going to do it about B. This will tell me the situation where moments are equal and the tipping is just about to happen. All right. Remind you that the width of this cabinet is 24 inches. So some of the moments about B, we have negative 12 inches times W, which is 120 pounds. That's the moment contribution about B from this weight W. Sorry, this should be positive. And the variable P, we're going to have a minus P times H. P is 36 times H equals 0. So the only unknown here is H, and the height now is going to be 40 inches. All right. So if H is 40 inches or greater, this thing will tip. If H is less than 40 inches, this thing will slide. That's it. Okay, so that's it for your two example problems. We'll look at belt friction on Monday, and that will be it for friction. So we'll see you then. Bye-bye.